Okay, so welcome back. And this is going to be the last lecture of this course. On Thursday this week, we're gonna have a Q&A sessions where you can ask any questions. I mean, it can be something related to exams, which I haven't said yet, and also can be something related to the course, or can be anything. I mean, like maybe just some career advice or anything. So it's it's an hour that I reserved for you, so you can ask any questions to me. Okay, so what we're gonna talk about today. So where we are. So we are in the still. So this is going to be the last lecture on the regression. And so far, we talked about something very basic about regressions. So we discussed various regression algorithms. The simplest one was linear regression. And then we also talked about rich regression, which is essentially, linear regression is essentially an empirical risk minimization with squared loss. And the rich regression is empirical risk minimization together with regularization term, which manages the complexity of models or of a hypothesis. And then the regularization was given by L2 norm. This is really ERM. And then we show that actually rich regression algorithm can be kernelized. So and that allows us to use rich regressions for, algorithm to come up with functions which is nonlinear. So we talked about kernel rich regression. But the problem, so when we talk about linear regression, it's a simplest algorithm which have a very nice theoretical property, but we move to the kernel rich regression. That's because by doing regularization, we can, the kernel rich regression has a better, generalization, better generalization property. Okay. Better generalization, but there was a problem. One problem is sometimes we want a sparse solution, which uses not all the information that's available in our setup or in the data set. We want some solution which uses fewer, small amounts of information. That's because that helps us to have a better, more efficient algorithm. Also, sometimes that leads to the better generalization. So that leads to what we're going to cover today, which are, so problem is it's not sparse. So what we're going to cover today are something called the support vector regression. And also we're going to talk about Lasso algorithm. They are designed to produce a sparse solution. So, so just to give us some quick overview, support vector regression is very much like kernel rich regression. Although we are using, when we do the loss, we are using loss based on L1 norm. It's very much like a kernel rich regression, but it uses the idea of not penalizing an example. Not penalizing a hypothesis with respect to an example, if the hypothesis predicts the example reasonably well. So in all the other algorithms, all the other algorithms, if hypothesis does not predict the example exactly, it gets a penalty. But in the idea of kernel this support vector regression, we are replacing this very hard requirement to a bit soft requirement, which said if your hypothesis predicts reasonably well, then we don't penalize. But if it performs badly, we start to penalize. And the idea of Lasso is very much like a kernel-rich regression, but when we regularize based on L1. So that's the idea. And then these ideas lead to the SVR solution. Okay, so let's start to look at support vector regression. So most of these algorithms, one way to understand these algorithms is to understand what type of optimization objectives these algorithms are using. These optimization objectives captures what the key ideas behind these algorithms. So let's just directly go to the optimization objective of kernel vector regression. And so the algorithm works like this. It takes the input, which is a sequence of input-output pairs. So it's a sample, which are a sequence of examples. So what 1, 2, xm, ym. There are elements of ym. And then because it's a regression, y is a subset of real numbers. So it's some space where we can measure the distance. And then what support vector regression algorithm, we're gonna write SVR. It's the following. It solves the following optimization problem. It's a primer version of support vector regression algorithm. So it solves the following optimization problem. The optimization problem is it tried to find a linear function. We find the linear function such that it have a regularization term, just like a kernel-rich regression, but its empirical error term is a bit different. So there are just some constants which balance, we decide how much emphasis we're gonna put the empirical error term, but then the empirical error that we are computing is a bit different. Say that for every predictions from our hypothesis on example xi, we compute its distance difference, its error for the input, the output yi, the ground truth yi. But instead of just computing this, the distance, or just difference between the two, we use a epsilon, in some sense, epsilon clipping, where the epsilon we give us some room of the error based on the epsilon. So that's the optimization problem that it solves. And here the terms, the absolute value of epsilon is defined like this. So maximum of 0 and y minus epsilon. So you can see that what this means is if the error of our hypothesis on xi is not greater than greater than epsilon, then we get the error is equal to 0. So this optimization objective is very permissive. I mean, it's not very strict on the empirical error side, but then in doing so, but the reason it does this is by using a bit less strict criteria for the empirical error, it can achieve the sparse solution. Okay. But then what SVR, the support vector regression, actually solved, support vector regression solved this optimization problem. But what it actually solved is something slightly different. That's because absolute value and this maximum, this absolute value with epsilon, it's a bit complicated term. And he rephrased that term in terms of optimization. So this happens all the time in the design of machine learning algorithm, which is if optimization objective involves some complicated, not very nice term like absolute values or this taking the maximum, often it is possible to rephrase all these things in terms of pure optimization. That's because optimal solutions, will essentially satisfy some extra constraint or satisfy some extra stuff that's imposed by this absolute value and this maximum operator. Okay. So that's what we are doing here. So this minimum turns out. So that's becomes the same as the minimum of WB and psi I and psi I prime. And so what intuitively psi I measures is the, it's a difference between W. Okay, I'm gonna write it first and then give you some intuition about what's going on. So the optimization objectives are the same, but for the other part, instead of computing something, some complicated term, we just said it's a psi I plus psi I prime. Okay, but then there is just some condition subject to the following condition. The condition is, say, psi I is greater than or equal to 0, and psi I should be also greater than or equal to prediction of our models speed minus yi minus epsilon. Okay, and then psi I prime should satisfy something quite similar. Greater than or equal to 0, psi I prime is greater than or equal to, in this case, it's a yi minus what our hypothesis said, psi plus b minus epsilon m4 or I in M. So that's the optimization problem. And why they are the same? The reason they are the same is because in order to, find the minimum solutions, the one below, then the minimum solution is achieved always when this psi I, because we have an objective psi I and psi I prime, psi I is minimum, and then psi I prime is minimum. Okay, so when psi I and psi I prime gets minimum, either they are 0 because that has to be greater than or equal to 0, and or if in the case of psi I, if this lower bound is a positive number, then psi I will become that number, and that's exactly, so let's use a spotlight. So if you look at this term, and in this term, if the term that you see here, the lower bound is greater than 0, then psi I should be that value in order to minimize the optimization objective. But if psi I becomes that value, then that psi I becomes the same as, this term. The term that you see here, that's exactly the same as this term if the term here is positive number. And in that case, psi I prime will become 0. And something similar happens for psi I prime. That means this lower bound becomes positive number, psi I prime becomes that lower bound, and then psi I prime becomes the same as this guy. And in that case, psi I is equal to 0 and so on. So I know that what I said is a bit confusing, but the point I'm making is that because we are asking we are interested in this minimization problem, the above minimization problem becomes equivalent to the below minimization problem. But then this minimization problem below is it doesn't involve any absolute values, and then it's just a linear constraint. And optimization objective is a quadratic function. So this is one of the very nice optimization problem. It's a quadratic programming problem, which can be solved by an off-the-shelf existing the optimization solver. Okay, existing optimizer can be applied to solve this problem. So that's one way to solve this optimization. One like a primer version of the support vector regression algorithm, which is solve the optimization that I just write it here. So that's this optimization, and then based on the solution of this optimization, return a hypothesis, which is determined by this WNP. Okay, so that's one way to do it. But this algorithm, the support vector regression algorithm, just like a support vector machine, allows a dual solution. And it also turns out understanding this dual solution is quite important. That's because it allows us to kernelize this algorithm. And at the same time, it allowed to see, something like a support vector appears here. It also allows us to see why the solution of the support vector regression is sparse. Okay. So let's try to dualize it. I need more space. Okay, let's see. I think it's better to do it space. Generalization. So here's the primer version again. I don't think I can copy. So the primer version is here, minimum WB, psi prime, square, C sum I, M, psi I plus psi prime, subject to psi greater than 0. So let me write this in a form. So we're going to use the standard machinery that we talked about when we discussed support vector machine, which is using Lagrangian. So to use the this Lagrangian technology, we formulate this optimization problems. We write this optimization problem in a form where this technology can be applied directly. So every constraint should be written as either equality constraint to 0 or something smaller than equal to 0. So we write it like this. And 0 W xi plus b minus yi minus epsilon minus psi I. And something similar, 0 minus psi I prime and 0. This time we write it yi first probability of xi is b minus epsilon minus psi prime or I. So we want to dualize this optimization objective. So how we do it? So what we do is that we introduce Lagrangian. So Lagrangians have is a function that have all the variables but it also have a variable for every constraint. So we're gonna introduce variable for the constraints in the above, alpha I for the constraint above, the alpha, use a different color. So alpha I for the above one, alpha I prime for the one below, beta I for the one, the other constraint, and then for beta I prime here. So if we do so, then Lagrangian take extra parameters, which are vector alpha, alpha prime, beta, and beta prime. And it's defined by just the objective that we already have. C summation I m. So this is the objective in the original optimization problem. But then it also includes a bunch of terms that's coming from the Lagrangians. So we have summations I is equal to 1 through m, where this C, write it here, and right here. So we have a term for beta. So we have a beta I minus psi I plus beta I prime minus psi I prime. They are coming from these two constraints. See there, so these two constraints. Then there is also a term that's coming from this big constraint, which is I is equal to 1 to m, alpha I, where multiplied to this xi plus dot 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 psi I. And then we have something similar for the alpha I prime. Now let's write it all because that helps us to see. So p minus I epsilon psi I plus alpha I prime yi w b of xi minus b minus epsilon minus psi I prime. So that's the quite complicated term, but it's very mechanical, so it's derived systematically. And then once you do so, then our original optimization problem, this minimization problem, becomes the same as the following problem. So the same as minimum over WB psi prime, and then maximum. I'm gonna ignore the issue of supremum, infimum, and so on, and just write minimum and maximum everywhere. So there's a alpha. So these Lagrange variable, the new variable that we introduced, they're all non-negative. And then we take a maximum inside, and then that maximum is Lagrange multiply, the Lagrangian. And so this is, again, there's something very, very similar. If we have some complicated term, often we can, so in this case, it's complicated constraint. often constraints or complicated functions in the objective can be rephrased in terms of different form of the optimization. That's what you saw in the previous page, and something similar is happening here. We remove the constraint, but because we are introducing some extra term here, that extra term together with this nested maximum, essentially encode a constraint as an optimization problem. So now, one interesting bit about this Lagrangian formulation is that the Lagrangian we have is a convex functions. It's coming from the convex functions, strictly convex function. Its constraints are all linear. In that case, this is a non-trivial fact. We can switch minimum and maximum. So that's in some sense, some new idea or some new insight is coming in. So, like this, in general, switching minimum and maximum, we get something different. But in this case, switching them give us same result. So we have a maximum over exactly the same value, and minimum over exactly the same variable, together with the same Lagrange. So this is, some non-trivial step. That happens because our optimization problem is good, and we also used this type of non-trivial step multiple times before. But then there is another. Write this. So we have this definition used here. So there's another thing that we are using, which is that now we analyze this optimal solution. So the alpha prime, beta prime, which is a variable in this maximizations, we try to see where the minimization can be achieved. And it turns out that minimizations, where this minimization can be achieved, can be, understood by looking at so-called KKT condition. That's also a bit obvious to you if you think about the minimization will be achieved when the derivative is equal to 0. So, red. So then we look at, so the minimization is achieved for this particular optimization problem that we obtained here. And when the KKT condition is true, the KKT condition said for L, when minimization is achieved, then the derivative of L with respect to all the original variables should be equal to 0. So W has to be equal to 0. Gradients of B, L should be equal to 0. Gradients of L with respect to psi I has to be 0. Psi I prime also has to be 0. Okay. But for these conditions, actually, if we work it out, and which is not very difficult if you just work it out, then it leads to the characterizations of W, B, psi I prime, and so on. Or it's give us some equation. If you apply that equation, we can get rid of this primary variable, W, B, psi I prime. So what does that imply? The first condition implies the following. We say that W, in the optimal case, is when minimum is nested, minimum is achieved, W has to be equal to the following form, minus equal to M to M, alpha I prime, B of xi. This has to be true. And for the derivative equal to B is equal to 0, this implies summation I is equal to 1 to M, alpha I minus alpha I prime is equal to 0. The psi I is derivative is equal to 0. That implies C is equal to alpha I plus beta I. If you remember what you saw in support vector machine, something quite similar. And then the last one is C is equal to alpha I prime plus beta I prime. Okay. So then now we plug in, and actually KKT conditions say a bit more. So it also says something about the dual variable as well. So, but I'm going to talk about it when we analyze the solution. Okay. So this is a KKT condition. Now, if you plug in this KKT condition, which said what W is, and then also we talk about some equations. If you plug in these KKT conditions into L, so then we can simplify L and we can actually get rid of this inner minimum. Because every variable, after plug in simplify L based on these equations, essentially all the primary variable will disappear. So we can have only outer maximum problem. So if you do so, this is the things that we can get. So this things. That's the same as we have a maximum over alpha and alpha prime. It turns out the beta also disappears. Okay, then the objective is written like this: so minus epsilon alpha plus alpha prime transpose the vector, which is just have a 1 everywhere, minus alpha prime transpose, and y. The vector y is just y1, y2, y3 up to ym. And the last thing is that alpha prime transpose. I'm going to explain what K is. So, and then this K is the ground matrix or Kernel matrix. So it's K is a matrix of size m by m. So dimension is determined the number of examples. So it really talk about how two examples are related, and the K ij is an inner products of V of xi and V of xj. And if we write this inner product as a kernel, then this is going to be K of xi xj. It's a kernel induced by V, and then that's if you apply the kernel on xi and xj, that's give us this K ij. Okay. And then it's under the condition that alpha I has to be greater than or equal to 0, less than or equal to C. And same thing for alpha I prime. And then the last condition say alpha minus alpha prime inner products with 1 is it should be equal to 0. Okay. So that's what we get after the simplification. Just plug in KKT and then simplify a little bit. Then this is the condition that you can get. I mean, which you can get very easily. Okay. So then one thing we can see is, I mean, that this entire optimization problem is phrased in terms of kernels and in terms of a dual variable alpha and alpha prime. So I mean, so this the support vector regression algorithms allows us to, I mean, it can be kernelized, and even when this B is infinite dimensional, so we cannot really compute B of xi, this algorithm can still be used. Okay? Because all we need to solve this optimization problem is just computing this kernel. So just like any kernelized algorithms, phi doesn't really matter in terms of computation. The only thing that matters is whether we can compute these kernels on xi and xj. For instance, we can use RBF kernels with this support vector regression algorithm. Second, Now, if we solve this optimization problem, but our objective is not to compute alpha and alpha prime. Our objective is to compute this function h. So optimal solutions, this is a function, linear function h, which is defined by the optimal weights together with optimal bias term B star. So the question becomes, how we can compute W star and B star, and how we can compute this H star in such a way that, this is again, the only thing that matters is this kernel. So we don't really need to compute this B. And that is also possible. So if you just plug in the W star, then the W star becomes something like this. 1 through m alpha I minus alpha I prime and inner products of phi of xi and phi of x plus b star. A phi of xi, phi of x can be written as a kernel. Okay, so we can move this and replace it as application of a kernel psi x. And then for B star, although I don't say this in much detail, B star can be computed to via, so the remaining part of KKT. And what that KKT condition tells us is if we can find alpha I, index I0, that's greater than 0 and smaller than epsilon c. And same thing happens for alpha I prime. So if we can find alpha I0 prime is between 0 and c, strictly between 0 and c, we can do something similar with that I0 prime as well. If that is the case, then KKT tells us the following. We say that corresponding psi I0 should be equal to 0. And then furthermore, the corresponding constraint, which is that W star, let's use the star here, W star and phi of x I0 plus B star minus y I0 minus epsilon should be equal to 0. Epsilon. The actual condition is minus psi I star should be equal to 0. So these are, if we can find such a the alpha I0 star, then this is true, and the other condition is also true. And by you looking at these conditions, we can first get rid of this part. So it should be equal to 0. And then also can kind of move B star and then simplify the rest. So if we do so, I think I need to do in place update here because I don't have enough space. So B star will become minus W psi 0 minus plus yi0 plus epsilon. Now we can also plug in the definition of W star there. So if you plug in the definition there, and this becomes like this. Minus summation of alpha I minus alpha I prime. M. This is inner products of V of xi, then V of xi0. And finally, we write this as a kernel. And if you do so, this becomes K of xi0. Okay. So in the linear function that we achieved, so which is written here, then we can plug in B, this part for B, and that will give us the solution here. So if you plug in B, and that will give us a solution. Now, so what can we say more about? So this is a dual version of the support vector regression algorithm. And then, so dual optimization problem, and then how we can read out the kernelized hypothesis from this dual optimization algorithm. What can we say about this? Can we say anything about something more about this algorithm? One thing we can say is that if you look at the alpha I and alpha I prime, yeah, if alpha I minus alpha I prime is equal to 0, that term will not contribute anything here. Okay, so alpha I minus alpha I prime is equal to 0. It's not going to contribute the computation of weights. Also, it's not going to contribute the computation of B star. So they will just disappear. A bit like some terms whose, in support vector machine, only support vectors matters because they are the ones who contribute the construction of a hypothesis. The same way, in this case, support vector is the one where whose alpha I minus alpha I prime is not equal to 0. So, and then furthermore, we can see when alpha I and alpha I prime is not equal to 0 from the KKT condition. So this KKT condition can help us to identify some case, not all the cases, some case where alpha I minus alpha I prime is equal to 0. So what's that case? So let's use some different color. So by the KKT, so a little bit more space. So then alpha I prime is 0 when this happens. Okay. And then some case when this happens is the following. So by the KKT, alpha I is equal to 0. Both alpha I and alpha I prime has to be equal to 0 if this condition is true. So if I will just use the hypothesis H star. If H star of X, Xi minus Yi, if their difference is smaller than epsilon, then this alpha I and alpha I prime has to be equal to 0. Okay, so we can plug in the definition of H star, and then they just see the Yi if they are determined. So in other words, if they close to our hypothesis, our predictions of the prediction of the hypothesis is not so bad. It's epsilon good. So then that's the case where alpha I has to be equal to 0 and alpha I prime is equal to 0. What that means is when the hypothesis make a reasonably good predictions, then those kind of data points, those kind of examples will not contribute the construction of our hypothesis. So because of this ignoring effect, this H star can become quite a sparse solution. So Okay, so that's, and now let's talk a little bit more about this algorithm. So then now we studied this algorithm. Can we analyze this algorithm? I think in the textbook it gave an analysis of this algorithm, but I feel it's more important to tell you about the relationship between this algorithm and the kernel-rich regression. So that's what I will focus more instead of this the generalization bound of this algorithm. So let's try to compare what we got with kernel-rich regression. So let me write down the objective of dual optimization for kernel-rich regression and support vector regression. So it's a kernel-rich regression. Your objective is written like this. You maximize alpha, which is not necessary. I mean, it can be negative. It says Rm, and the objective is R transpose of Y minus transpose. It's the same kernel matrix, the ground matrix, and lambda I. Okay. And I said this lambda I part is really coming from the coming from the fact that we are using squared loss. Actually, I mean, this lambda is not squared loss coming from this regularization term. But let me write down manipulate a little bit, because I mean, this is not exactly the maximization, but it's essentially equivalent if you just remove this half and put a 1.5 here. And now for the support vector regression, it's a dual optimization problem is written like this. We have a maximization alpha prime, and we have alpha prime minus alpha. Let me see. Right. Alpha prime minus alpha transpose y minus alpha prime minus alpha k prime minus alpha minus epsilon alpha and alpha prime transpose 1. And so there are some conditions. The condition set C and I prime, we have something similar. And there's some condition about prime transpose 1 is equal to 0. So, I mean, it's maybe not exactly the same form as the one that I showed in the previous slide, but it's just, I mean, it's the same thing. I mean, instead of writing alpha minus alpha prime, I use alpha prime minus alpha and so on. Now, if you compare these two, they are not the same, but there you can see some correspondence. Okay, so if you map, because I mean, all these alpha i's has to be positive. I mean, ignore the upper bound at the moment. So if you map this alpha and say that alpha is essentially in the KRR correspond to alpha prime minus alpha, because if you take two non-negative numbers subtracted, then you can essentially express any real number. Like this. So then you see that the first part looks essentially the same. I mean, the first part is about this. I mean, they are essentially the same. For the second part, they look quite similar. Okay. I mean, except that the use of this lambda I mean, that's because actually that happens because in the KRR, the empirical loss was a squared loss. In the SVR that we talked about, the empirical loss was based on just L1 loss. So we didn't really square the loss. So that's why the difference happens. And there is some extra term. And also there are some bunch of constraints. I mean, it's a different color. So there's just some extra term here. And then there are also constraints like this. And then let me mention that the last constraint, this is really coming from the use of bias term. When we analyze the KRR, we ignore the bias term. We said that bias term doesn't exist. So in some sense, this last term doesn't really count. We can ignore it in some sense, because I mean, that's the part which they didn't really appear when we analyze this, when we define this kernel-rich regression. So if you compare these two, then what the key difference lies in this extra term here. And then the upper bounds, so on. And in fact, the key difference between support the vector regression and kernel-rich regression is really boils down to this extra term. I mean, that can be seen a bit better. So let's use the support vector regression 2. So what that means is when we did a primary optimization, so we said primary optimization was written like this. Let's see some. So in the primary optimization, we just take a psi I and psi I prime. Suppose we square it. So that's what we mean by SVR square. Then if you do the dualization all the way in the same way that we talked about, then its dual version will look like this. Then we have prime transpose y half. Let's use some different notation. Instead of using C, suppose I use 1 over lambda here. Okay, so lambda is any positive number, so you can essentially, instead of writing C, we can use 1 over lambda without any issue. So if we do so, then it has the following form. Lambda I prime minus alpha epsilon. Okay, so now you can see the difference much more clearly. So you mean the yellow part in the objective is exactly the same. Yellow part is here. And then for orange part is again exactly the same. So the orange part is for KRR and the orange part is support vector machine square. They correspond to each other. And then for we have a R, which can be any real number, and then I mean having two non-negative real number and subtract them, we can essentially express any real numbers. So and then I said so the key difference between you can see now the key difference between two algorithms, the key difference boils down to I mean this extra term. And as I said, the last bit I mean, because that comes because of the use of the bias term, so we can ignore this. So the key difference really boils down to this extra term here. And also another thing that you can see is if we set epsilon to be 0, then this support vector regression becomes essentially for this quadratic version of support vector regression becomes the same as Kernel-rich regression. So support vector regression can be understood by looking at this dualization, can be understood as a generalization of Kernel-rich regression algorithm. And there are generalization bounds about these algorithms, and so then inform generalization bounds. So I suggest you to take a look at a textbook. So I mean, it's a very easy consequence of two things. One is about the theorem 11.3, which give a in some sense very generic generalization bounds for regression algorithms, which involve Rademacher complexity, and then of a hypothesis set, together with the Lipschitz constant, and then some bounds on the loss function. But I mean, if you compute the Rademacher complexity, well, bound the Rademacher complexity in Lipschitz constants and so on, then you can get a generalization bound for support vector regression and this squared version of support vector regression. Okay, so that's for the support vector regression. So let's move to the remaining 15 minutes. Let's move to the last topic, which is the Lasso. So why aren't we done? So actually the reason we are not quite done is because the support vector regression has some problem. So first problem is we have to set up, it has a hyperparameter like epsilon and c. How to set is not entirely clear. And this is well, I mean, it's not really major problem. And it's this kind of hyperparameter appears all the times, and then like setting, not easy, but can be done. A bit more bigger problem is, I mean, the support vector regression, I think main use is in the dual form, which is phrased in terms of the, I mean, it's complexity depending on, highly dependent on the number of examples. Okay, depend on M, and then its complexity. So computationally, it's not very efficient, especially when it's not efficient, especially M is large. I mean, not efficient. I mean, not if the optimization is not efficient, but perhaps more importantly, the hypothesis, the function that we came up with. I mean, it's that the time to compute the predictions may depend on the number of examples, and if the number of examples is really, really large, even though we are trying to come up with some sparse solutions, then still the computational complexity of computing the hypothesis may be not so like I mean, it may be reasonably high, so which we want to avoid. So Lasso is designed to address this issue, and the key idea of Lasso is Lasso is, I mean, the Lasso is an issue as well, but it doesn't have a natural dual form, but so it's more focused on the primal form. Focused. And then the idea of the algorithm is really simple. The idea is to solve the following optimization problem. So WP. But then the optimization objective uses a regularization, but the regularization we are using is L1. And for empirical loss, you just use the squared loss. So this looks like very similar to the kernel ridge regression. So the key difference between this Lasso algorithm and the kernel ridge regression is the use of this L1 norm on weights. So this L1 norm definition means that, so it's K. And it's just the absolute value of each component of the weights and then just add all of them together. Okay, so that's the L1 norm. And then it turns out if you use L1 norm, then the solutions tends to be very sparse in the sense that the weight weight component of the weight, which is non-zero, is not very large. Okay. The reason, I think the showing this exact formally requires non-trivial perhaps analysis, but we can gain some intuition quite easily. The reason that two ways of getting intuition. One is that now suppose that we are kind of imposing some constraints smaller than equal to say lambda, imposing a constraint like this, and solve the optimization problem of the second. This is not telling you, it's not a mathematical explanation, it's more like intuitions. So suppose we have this constraint and solve the optimization problem above for given the sample, which is x1, y1, x2, y2, and so on. So then we can ask, so suppose that W is two-dimensional, W consists of W1 and W2. So it's in 2 dimensions. And this constraint that I just wrote here correspond to the diamond constraint. Say W is in this region. So W has to be inside this region. And then now the optimization objective, which is given here. We can do the, we can write, I don't know the English names. In Korean, it's called 등고선. So we can write down a graph which say that the value of this optimization objective is equal to 0. So that's because it's a convex, it's going to be some circle like this. So where the objective is equal to maybe 1. Objective is equal to 2, maybe contains this 1 that may be larger. So it's a 2 and so on. But then in the convex case, the place where the minimum happens under this constraint is usually at this corner, okay, corner like this here, okay, which maybe the objective has a value maybe 20. The object in this optimization happens at this corner. So that's why, intuitively, that is why if you use this objective, then often the answer is, the solution is sparse. That is because, this type of optimization that I just explained to you, the optimal value is happening at the corner right here. And another way to gain intuition is to think about these functions, the absolute value function. You compare the absolute value function together with the square. So if the value is equal to 1, so this is W, not W, say A. And then if we have a square, then in the beginning it's small, but 1, it becomes 1. Then it's growing quite fast. But so this is square. But then if the linear functions goes like this, okay? So when the value of a is larger than 1, the growth is, the linear function is smaller than the a squared. But if value of a is smaller than 1, the value of a is larger. So this provide a stronger signal. So if you want to it's not maximum, it's a minimum. If we want to minimize, because the value is larger here, we get a higher segment that this optimizer try to reduce this value of w much more aggressively compared with when the situation when we are using this squared the L2 norm as a regularizer for w. Okay. So these are the kind of two intuitions about why if we use L1 regularizations we get a sparse solution. Now, so this is a Lasso algorithm, but just like before, this absolute value is sometimes not very easy to deal with. So, instead of solving this problem directly, typically we solve some massage problem, which is equivalent but has a better behavior. So what do we solve? So it's a bit like the user idea that I told you before. We split, instead of saying W, the real vector W, we have two non-negative real vectors W plus and W minus. They together represent W, but if you have a W plus and W minus, absolute value can be easily represented. So here, we have a minimum W plus, which is the vector, but it's greater than any of each component is greater than equal to 0. So that's a vector greater than 0. W minus is also greater than equal to 0. And we are taking the B, we are taking the minimum with respect to this guy. And for the lambda, but for the absolute value, we replace it by this. Okay, is equal to 1 to m n, and so W plus W minus. And then the rest is very similar. So W plus minus P of xi plus P minus yi squared. So you can now see that the constraint, these two things are equivalent. So intuitively, W plus minus W minus, so this term corresponds to W, okay? And any W can be represented as W plus minus W superscript minus, okay? And then the one below, this minimization problem below, in a sense, solve minimization problem over the larger domain, but this extra bit doesn't really matter because at the optimal points, there is, in some sense, one-to-one correspondence between W and W superscript plus, comma, W superscript minus. Okay. So there's a correspondence between the two. And then it's essentially the same idea as what you saw in the previous case where we use replace this absolute value subscript epsilon by psi I plus psi I prime. Okay, so these are equivalent. And then the one below is a nice optimization problem. It's a convex optimization problem with a linear constraint. So it can be solved by off-the-shelf ion optimization algorithm. And that's the idea of the Lasso algorithm. Okay. Now, remaining 3 minutes. let me mention one more things. So then, I mean, according to the textbook, it's very difficult to realize this Lasso algorithm. I don't know why, but the textbook says that it's very difficult. So very likely to be true. And but one things that the textbook talk about is for this lasso, we can also come up with a generalization bound. And then to show the generalization bound, mainly, the general scheme is the same. We use a theorem 11.3. The theorem say, okay, I mean, how we can bound any of the regression algorithms. Then we end up with bounding Rademacher complexity of a hypothesis set, and then Lipschitz constant of a loss function, and then bound on the loss function. So if you have computed three things, then by plugging them, then we get a bound. But the interesting bit here is that about this Rademacher complexity. Typically, the analysis of the Rademacher complexity in this entire chapter is based on the L2 norm. So what is the hypothesis set? The element of the hypothesis set is a function like this. We ignore the bias in the analysis. Something like this. So typically the bound is happening with respect to L2 norm of W. So we said L2 norm of W is bound by lambda, and we bound the Rademacher complexity using L2 norm. But in the case of, so that's the typical scenario. But in the case of a Lasso, this is not very satisfactory because Lasso doesn't really optimize L2 norm of W. It optimizes L1 norm. So which I write it as a lambda 1. So then question becomes, can we write this bound on the Rademacher complexity in terms of L1 norm? That's theorem 11.15. So the theorem say the following. So it says that so suppose for every x in our input space, we get the feature map is a sup norm, which means maximum. Of any component. I mean, if you are familiar with the sup norm and L1 norm, this sup norm is a dual of L1 norm. So this is bounded above by, say, R infinity for some fixed Rm. And then the second condition said if our hypothesis set consists of linear function such that it's L1 norm bounded by lambda 1. So if that's the case, then the Rademacher complexity of this hypothesis set H bounded by square root of n this L1 norm square, and then the R infinity square 2 log. So if we just give me 1 minute, then I'll be done. If you compare this with the other case, where instead of this infinity norm, suppose we do the same thing, the L2 norm, and then also this one, L2 norm here. So then in that case, the bound was like this, was n lambda 2 square r2 square. So it looks like, I mean, if you see, compare these two, there's just an extra term, this one, and then you may think that, okay, we don't gain anything. And actually that's not true. So if you look at this definition of these two, what is R2? I mean, this L2 num square. I mean, this L2 num square involves, give me 1 minute, then I'm really done. This means that it's a sum of I1 through the components n, okay. And then there's all the components of p of xi square, okay. So square root of this guy. So on the other hand, if you look at the one below, this is just a maximum. So when you look at the one component, okay. So roughly speaking, what is missing here is because we are only looking at one component, n component is missing. So roughly this term, is correspond to n times, although the n times are infinity square. So now if you view it from this perspective, then you can see some gain. So instead of having n below, we now have a log n. So that if you just analyze the generalization bound directly by exploiting this the L1 norm, then the bound becomes tighter by replacing the linear dependency on the dimension into the logarithmic dependency. Okay, sorry about overrunning the time, and that's the end of today's lecture. Actually, that's the end of all the lectures. And then on Thursday, we're gonna run the sessions mainly based on the Q&A. And thank you all for taking this course. And also, this course was not very easy, but I'd like to thank you all for taking so much time and following the course. Okay, thank you very much.